Okay. Okay. Because you asked, like, we have three situations, like, about what's the program, the IO, and second one is the interrupt-driven IO, and the direct memory access. So back to the one, what is that direct memory access? Is like we are not, the processor won't involve in this product access. Okay. Mainly why? Because like you can see what's the large volume data going to move. Just like make it simple, I saying the really simple example, maybe if you pop in your USB drive and copy the file from your C drive or D drive to USB, do you think this will require the processor to like get involved to the copying file? Actually, this simple, really like good example, I think. Get it?
Maybe to start it.
Okay, so what we need to do, I tell you, like, most of the time the driver, all the different memory storage, we have the set of it, we install the driver. So driver is the modules we say in this, like, the in the lecture. So they are helping us to manage all these like access and reading. And when for the large file movement, like copy and paste, or like you cut it and paste it, no matter which way, because we do not require calculation, like possibly like change the data, we just like move from a place to this place. So we let the driver or the modules like communicate by itself. It's like keep sending, receiving. That's like how it works. Okay. And back to the one is like interrupt driven. So what's the, sorry, you need to ask again. So what also like what makes you like confused? Because I think you take the examples like program the interrupt.
I guess the question was, in direct memory access, it's just going from my flash drive to my hard drive. So it never passes through my processor. Okay. I wasn't fully understanding, because I assumed that the processor would be involved in all three.
Okay, yeah. For the last one, the processor is not really involved because for like copying data, we say moving. So that's why we call it direct memory access. So it's like we directly, but not through the processor. That's how we because coming slides we talk about the OS, the operating system, like helping to manage all these things. Because processor also is just like waiting something to fit into it. So it's not the actively like it's not really like actively asking for like give me something I need to working. So we have the status called idle, it's just like nothing to do. If we didn't fit something, like give the instruction to the CPU, then it's just waiting over there. And most of the time, why we are adding cache, like they don't like for the architecture, got this one, it's like part of related to the architecture. Because the processing speed is really fast. So it can finish within 1 nanosecond. But the memory, the main memory, or the storage itself, like getting data, is really slow. So most of the time it happens like, okay, the processor finished the job, it's waiting for next instruction. So it's tend to like just like idle status, like nothing to do.
So it's like, so flash drive, hard drive, instead of the operating system being like, okay, CPU, we're gonna pull the data from the flash drive to the CPU to then put it on
In the flash drive is
the operating system just directly pulled it from the flash drive to hard drive.
Not this one. This one is talking about the direct memory access, right?
Yeah.
So. Okay. This one is not about the process because only copying, so it doesn't, just like thinking assign tasks.
Yeah, that's what I'm saying.
Yeah.
It doesn't need to go through the processor.
Yeah, the processor. Okay. And when I talk about the access, because the speed it affects, that's why we have the level 2 caching, level 3. Try to let all the speeds like. Actually, we add more hardware to let the processor like have something like adapt to that processing speed of the CPU. Yeah. So, and then we try to keep more cache and make it like, let the processing speed or resource like utilize better. That's how we design. And sometimes when we like we have some task like instruction. So for the rest of two program IOs, that means like we are expecting for input, maybe like keyboard like ask for input. So when you're writing a program, so we need to maybe see or something, we have an input, right? Asking for input. So the program will wait over there for it. So we know we need for some input. But sometimes we have like keyboard shortcut. Like when we have some like command C. Also the one maybe we are using SSH to something if we want to stop. So we can have some shortcut to terminate it, right? So they are interrupt. So when they detect their certain like key combination, it kicks in. Okay, so the IO will detect this key combination is like one of the interrupt. So this interrupt will send it to a step. Okay, so it will go so it will like stop the current instruction. So they run the interrupt instruction as the next. Okay, maybe this one is to stop the program. Then it just jump like skip out the one. So if you remember the diagram, like say x plus y plus 1, so we already jump like skip this program. So we will go back to the like next program we're going to execute. That's how the IO like different IO. I wish it became more clear. So okay, it's all good. Okay, then today we will move on to talk about like some key function like about the OS. We need to know like kind of like summarize and describe the key function and design the objective of operating system. So what's the operating system? So we free and then manage and share the resources, protection, isolation. It's really important task. I remember you asked the question like especially you mentioned about you have a question about the PC program counter. So why what's the example, the demonstration simulator is start from 0, right? But sometimes if from the PowerPoint you see that we start from 300. Do you know why the program counter like actually it's not, I say it's not always start from 0. Actually suppose it shouldn't start from 0. Don't know why.
The operating system. Or,
Yeah.
Like the program counter will go up just from the computer turning on with the
Yeah, we already like preload lots of things. That's a reason why we need operating system. So when we press the button, turn on your computer. So what it's doing? So it's first go to grab the operating system, load it on the memory. Then we know, okay, then we need to start to, okay, so how to manage all the resources. We are checking, okay, what's the status of the CPU? And then is any new instruction coming in or something? That's how we do, okay. And also it try to provide clear, easy, like using abstract physical resources. So how many memory or like dedicated machine or like high level, how to access the files, like manage the user, some message, and also like masking limitation or like virtualization. Common surface, like we have to handle the surface, the Windows system, networking, sharing, authorization. So all this will like how basically this is a manager, like your assistant, take care of this like physical device. Okay, so this is a really special layer of the software. Then we can provide the application software access to the hardware resources that we say, and more like convenient abstract of the complex hardware devices. And then we can protect the assets to our shared resources. Mainly one thing is that we, before we talk about the IO, the processor, the memory, we are not really touch it. Like say, okay, let me assign this program to this memory slot, or let me change the processor instruction, like jump to this one. We are not able. They say always like protect is like something when you look at your Windows file, because Mac they always have better protection, so you cannot really access some of them. But when you look at the files or a temp or application file, so you can see all this. Okay. And sometimes if you delete one of the file or change the SSY, you make it like corrupt the application. So it's like more like security, and also increase the help us to like communicate all those like logical entity. Also logical entity would be like all those like gates, the gates right here. So it's like more like physical hardware. Okay. And like changing. Okay. So as a OS, so it's a program to control the execution of the application programs and agile interface between application and computer hardware. So make it more like convenient, repeat again, and efficient. It's important because we have lots of resources, like the hardware resources, and then as some software they're waiting in the list. So we need to know predict, okay, is it enough, sufficient to use? And we need to like free up sometimes your question. Okay. So when we have how to manage the memory, if you learn Java, you have the called the garbage collection. You know the terms, like anybody know what's a Java or learn Java? Oh, okay. A kind of, okay. So if you know, I say garbage collection. Like based on this one, what would you guess? What's the usage of this one? Actually, when we load all those, like when you want to execute a program, so we load everything on the memory, and then when you try to like create lots of variables, A, B, and then C, and then like number 1, 2, 3. Okay, we create a lot these variables. So when we create this, it may occupy if an integer like ABs, and then like the byte, or like if it's a letter, 2 bytes. And if you only use once, or like after you use it once, you never use it, how are we going to handle it? Because if you are not going to like remove it, you always like occupy the space of the memory. Okay. Because sometimes like program to program, they don't know which like location is available. So it's the OS, the manager, okay, I know this area. Sometimes they will try to like Java itself will detect, okay, there are some variables available, suppose I should remove it, like I should free up the memory. So it's kind of like this, okay, the OS2, we need to know, okay, if there's some they're not using, that I need to free up the memory, then let I can assign or allocate those resources to other program. Okay.
So it's the same idea. So I mean, I just know C++. So like you have variables and everything. So, but once the variables go out of scope, then that's when the OS can go in and free up that memory.
Or sometimes they will detect like is this because when you loading all the instructions, they'll know, okay, is this variable are going to use again later, or are you like going to use it? Sometimes you create a temporary variable, like have to like fix like number 1 plus number 2 and put it as 3, and then you're not using it anymore, and it's just like display as output, and that's it. After the output, then are you keeping holding this like temporary memory, like to say this variable?
No,
like,
yeah, because once you're done with it, then if it's out,
yeah,
then the OS goes in.
Yeah, so it's like try to detect all this, and that will remove it. Yeah.
Constructors and destructors.
Yeah.
Okay, yeah. So you know that.
The OS will go through destructive.
Yeah. So it's the idea, like that's why we need it. And you see right here, like the software complexity always actually it's not linear, it's exponential, it's like really going up. And so you right now, even you we say the OS, maybe before it take like 2 gigabytes, and then we start from the Maybe you have a like Windows 98 XP and Vista, I think it's not really good. And then Windows 10, 11, all this. Okay. So because they provide more features, so they were getting more like compact. Okay. And it takes more gigabyte to store. So you will see always like when you have if you try to install or like embed your own computer, so you have, let's say, a 1 terabyte hard disk. And but after you install your OS on it, you will see the storage, it goes down. That's why it happens. So it really takes like more functions, more features. It takes more complex. And actually, like every piece of computer hardware is different. So maybe the CPU, most pretty common, I think right now we have the ARM, now we have new one is the Apple, they have like the M2, M3, they changed the structure. Windows, we need to handle with the AMD and Intel. So they are like, because their structure, like even itself is different. So as a OS, we need to manage, like, okay, if we have, sometimes they need to communicate with the really like physically with the hardware. Then how can we memorize? Even we transit from like 32-bit to 64 bits. Do you know the terms like 32 bits OS and 62 bits? Do you know what's the difference between these two? And because also it affects the OS. Because right here we talk, because like 32 bits, maximum will be, we can use 4 gigabytes RAM. Okay. And I said more, if we change to 64, then we can use more than 4 gigabytes, more than that. Okay. When we change the hardware standard or the OS like supporting version, then we can see old school, like really long time ago, older than me, then we are using like 4 gigabyte, like 42. And even you want to say, I want to upgrade my RAM to 8 gigabyte, but you only can use 4 gigabyte. That's it. Then you are waste the remaining 4 gigabyte. You're never able to, as I go over that. And that's why we need to like upgrade the CPU so we can like support the different hardware. Okay. Right here in the like as an operating system, so we as a like resource manager, you see we have the computer system inside. We have the memory, and then we have different I/O controller and the processor. And those I/O controller, we will connect to the I/O devices, like printer, keyboard, maybe some camera, like webcam, all these like possible. And we also have a storage, connect to the storage. So they will like manage all these resources of the computer. Okay. So also we will provide a useful abstract. So have like process a virtual machine, and we have the VM infinite memory. You can decay, but it's a infinite, but depends on like where, yeah, hardware. And also high level object like file users, some sending message, all this. Now back to we talk about the TCP/IP. So handle all this like abstract thing API. And all the programming like simplicity, like each process just think, okay, we have all the memory and CPU time. So we all say memory, CPU time. And all the process, they all like, it all have like connect all the devices. Yeah. So all the different devices will appear to have a like same level, high level. I say it was a high level interface. And devices interface are more powerful than more hardware. What's the interface right here? So the interface, like because we have the hardware, we have the connection. So it's the same as an interface, like helping to connect if the IO device connect with the like the pub to the, maybe some IO we are using a USB, or like right now we change to Type-C. And then we have the bitmap display will be the do the Windows system is the bitmap, do know what's bitmap? Yeah, so you know, right? Because okay, so for all the systems, guess what was bitmap? Yep, yeah, just like that. Yes, good. Yeah, it's like, and then we have the Ethernet card, so we handle the like TCP/IP. So they're all the interface that help us to handle it. And for isolation, so sometimes like some process they cannot affect other process. No idea this one, and bugs cannot crash the whole machine. So you see right here, this part is about the OS. We need to let's say process can be the part of the function of your program. So can your process directly, let's say, okay, I want to change this process instruction? No, you cannot do that. So you're mainly like if the process itself executing your own instruction, so the OS will say, okay, you do your own, but you cannot like affect others, or like if you try to access, sometimes they more likely affecting, maybe you change other memory doesn't locate it to you, or like it doesn't belong to your program. Suppose you're not allowed, sometimes they overflow, or like it's not working at all. And we are trying to like prevent the bugs cannot crash the whole machine. Is okay. Bugs can be like the program, this program itself, right? So most of the time when it pops out, you will see the program, it just execute. That it just quit by itself. Right? Sometimes when you double click, it's execute, but it won't say, okay, your window will be crashed. You cannot like, when you open a music player and over YouTube, is the music player crash. Suppose it won't affect your YouTube, like keep on playing, right? So like this. So this is how the OS I try to do it. And then protection and portability is like, okay, so make sure the interface is safe and stable across many platforms. So just like make sure like when we connect all these interface together, and then if sometimes like this USB or like one link have some issue, suppose it won't affect others, maybe my storage, maybe my display, or like my keyboard or mouse. Suppose we shouldn't able to, unless there's some virus or somehow that is apart from that. Okay, so right here for the key infrastructure, one is like for the ISA instruction set architecture, application binary interface, and application program interface, and then the glue, the system itself. Okay. We can see the similar diagram right here. Always like on the top is the application program. So all those like what we see will be the application. And for the application, sometimes we will call some libraries. It's like you call the utilities. Library, because when we implement, let's taking, if you are writing some program, we're asking for input, right? The keyboard input or mouse input. We didn't really implement by ourselves. So they already have some library. Or sometimes they simple as some like functions. We just call it like shorting. We can implement our own shorting, or sometimes the application like or the program itself, it provides a shorting function, kind of similar. So we have the library. So they're on top, like we need to record. And then right here, you can see the operating system within this layer. So you can see the like on top, we have application library, and really goes down is the operating system. And operating system still belongs to the software layer right here. And the software, as a bottom foundation of the operate will be OS, and OS will be directly help us to communicate with the hardware. So it's like manage all those, like we're checking if we have an instruction. They say, okay, load this one. So the hardware is sending data from the system bus to the from the storage to the main memory loading to the processor. If the processor finished the calculation, then we send it back to memory. So based on instruction, then in the hardware layer, some driver or modules will handle this part. Okay. So far for the OS stage, like the history, like we will know, it's called the batch system. And then one is more like complex multi-programming virtual memory. Really long time ago, the batch is really a batch. They need to like have kind of like backup. Have you seen some like picture old days ago, how the OS it work? They call the batch system. So it's a really huge big computer. So when you need to pull up the instruction, you need to pull it out and they push it by yourself. So it's really like that. And of course, like after the OS like keep improving, changing, so we're getting more. So like the serial processing and then change the simple batch system. And then we including the multi-program and also the time sharing system. Right here, I think it's a small one right here. So they are really big program. Okay. Okay. So what's the serial processing? So in the earliest computer, like we call it computer, but like based on our current standard, they are not really computer. Maybe it's just a calculator. Okay. So there are no like operating system involved. So really they need to interact directly with the hardware. So say you have to pull it out and then push it back. If I need to calculate the math, just like pull it out, pull it back. So all the computer just like running on the console, they're just like showing like, okay, it's working, it's no asking for input. And why now is like, okay, we need to handle if we have one thing is about scheduling. So when you have like so many tasks need to use, then how can we schedule it? And also like time allocation, how long does it run? How short? Like if I have multiple process, how can we allocate the time to manage all these processes? Do we setting timeout? So here's the time. And then later, when we move on, then we have a simple batch system. So that time, I think one computer, like maybe really expensive, I think it's more than 1,000, 2,000, even the first version Apple. And therefore really huge monitor. So they only able to see the output. So slightly background history of here. Then when we need to monitor the point of view, so right here you can see for the monitor, you can see all the like interrupt process and then the device driver, job scheduling, and then control language right here. And they will say the like user program area. So it's really like old school computer, like with kind of like simple, not really including the OS to help us. And as a processor, like they will execute the instruction from the memory that contain the monitor, and then they will execute all the instruction in the program file until it end of it, or have some error occur. Nothing special. So just like control the jobs, like assign one by one. So it's really old school style. So no matter it's like the monitor or the batch OS, or like just a really simple computer system. So far, can we doing like those like memory protection, timer, privilege instruction? So it's like user input or the kernel. So the kernel is like more likely the system itself. And how do we handle the interrupt? So we need to like fix it. And those like processor will alternate between the execution of the user program and execution of the monitor. So you will see those like monitor will be included devices. And so far, if we are doing like this, we need to sacrifice some like memory to handle this like monitor, because for all those like devices stuff. And also some processors need to like consume the time. And that's why it comes like why we do have like take it out as the called modules or driver. They say, why we taking the memory that occupy, just like doing something like checking status of IO. So we take it out from it. Okay. And basically when we try to utilize with the like problem with simple patch, just to let you know, it's like really taking really slow, and the idle time, just like keep waiting for all those like income. And after that, we start to move on called the like unit programming. So when we have a program, so we will execute, we have one time, then we will wait for it, and then it will execute and wait for it. It's called a unit programming. So when you see just thinking one CPU, just execute one program. So sometimes we need to waiting for input. Maybe we execute like few instruction, then we need to wait for like fetching the new data, and then we execute. So we are not really utilize the CPU's processing time. So then we need to think, okay, then how can we make it better, like handle multiple programming? So maybe later it comes out that like this is an early stage, like Microsoft, the docs. You know, the docs also is a command line, like when I input, like taking instruction, kind of like thinking the Linux system, kind of similar to that. And it just like get rid of the concurrence. So only always one time. And later when we really move on to the multi-programming, so we have the Linux, you can see, and then from the Windows NT, I never use it, Windows 8. And Mac OS, right now the Android, now all our days called the multi-programming nowadays. Multiple programming, that's we need to learn, or like we mainly focus on like how to take care like multiple tasking. When we have multiple programs, process, how this OS to handle it. And because when the memory can put all different programs, then how can we assign? Let's say this is a really we are going to study about this part. Is like if we have two programs, most of the time we have like we will execute one part of it, because we will break it down as a block, like, or instruction. So we'll execute part of the program A, then we will execute the program B, and then take in turns and wait. That's like how it actually works in the like nowadays the OS. And of course, right now we have more than one program, like multiple programs. So it keeps switching. And then right now, even one program we will go back. You can see a waiting time, the gap right here. But actually in reality, actually it's non-stop. So like the other time is really shortened, because we have maybe program A, B, C, D, like that. Okay. And here you can see the time, like waiting time, the CPU and memory. So most of the time the CPU right here, it processes, waits and jobs, wait. And memory always like low performance. When we need to load the content, it goes out a little bit. And when the load fetch is done, drop a little bit. Disk always like in the beginning, nothing to do unless we really access, it just like suddenly operate a lot, because we need to load all the contents to there. Terminal always like involved when we need to like load the resource to the memory. Yep.
So
we
go back one
here.
here.
Okay.
It says that in order to run two at the same time, it has to be able to hold the memory for both. Does it do that in the cache or the RAM?
Cache, oh, we do have holding part of it in the cache, because RAM will be saving all of them. Like if we have like two program A and B, well, we need to execute. So suppose we will load two program to the main memory of them. And because for caching, we are like saving the previous. So maybe part of the program A and part of program B, we're saving in the cache. Because the CPU right now is like more like it's like going back to access, right? So I will handle process A, so I'll go to cache to get the process A's like part of it, the bulk information load it, finish, send it back to cache. And we do have some policy, or like we can say okay, after we process certain time or when it's full, then like we will like remove or free up some, like are we adding the new one, or like we move the old, save the memory, replace it, then how we do it. So suppose that we are saving all these like frequently used, including program A and B in the cache. Is that your question? Okay.
Is it more like whenever we run A, the cache will be mostly A, and when we're running B, the cache will be mostly B? Or is it usually split pretty fine while we're going through the whole process?
Suppose it should be pretty fine, because when we are loading a multiple program, make it simple. Right now it's 2 programs. Suppose you will see it's like because they are taking terms like 2, so they should be split to half. But in reality, actually, it's not really only 2 programs. So maybe let's say 10, then they will like have 10 programs like waiting over there. And because they will like have an execution cycle. Also, there are some program instruction, like some process will finish earlier. So they will kick out. So once it's done, it will free up the space, we'll replace it. So in certain amount of time, like some because they will arrive late. Like I will finish it, some will arrive late, then it will free up the space. So I say, if you only cut in certain time, it's supposed to be used eventually, should be same, but sometimes the length of the process, it may be like kick out earlier or finish earlier. So then we won't be the same. To get it. Yeah, it can be 0. So so for your question, like really depends on like which time. Maybe times equals to 0, maybe no process, nothing. Maybe time equals to 1, only 1 program, 1 process, it comes in. So 1. Okay. So right here. Yeah.
If you're back on the last page of the disk, if it's
This one?
this,
This one.
yeah.
Okay.
Should it, what it would be a good, like an optimal percentage of your operating system is managing the disk?
Percentage.
I don't know how else to say. So like, how is it, let's say your disks at 75% almost all the time, is that? Does that mean your hardware or your software is together?
This one, the percentage right here is like the I would say the resources, like how much resource is taking like over that part. If the disk like what is fully utilized, because we are loading sometimes in certain time. Let me see. I want to show you the activity monitor right here. If you look at here, so basically right now I have some you see all the application, like we say the process, the executing. Where I'm running the Zoom is like taking, so it will have some like interrupt with the IO, so it can like goes up, down. This one, the time is like based on what it's doing right now. So if like it's like completely loading all the information, so it will maybe taking 100%. But that one doesn't take all those like read write right here. So you can see right here, then it may be not using 100%. So is it the one you want to ask?
Yeah, I don't know.
Yeah, well, for the IO or right here, you can see the memory right here in this moment is flat. Okay. Well, we are already like occupy parts of it, but we are not adding some new stuff or cancel the stuff. So the memory just holding flat. Okay, so you can see the percentage. It doesn't show the percentage. But you will know the total right now is used like 16 gigabyte. It's just getting fat. So nothing changed. And CPU right here, there's some operation still taking, so it's like executing. So you can see the line is using. And okay, zoom, it comes out, it pops out a little bit. So you can see it move, but it won't like, it's not taking 100%. So you can see right now it's still like idle, nothing. So 95, almost like 90% of CPU is not doing anything. Even though you see I just like using Zoom, also like opening the PowerPoint and maybe some like files finder, or like we also have lots of like background process. You can see a lot right here. So we are still not yet like utilize all those. Like, of course it changed, like sometimes because like in certain time, there's some events comes in, so it will ask the CPU to do it. So it kick in. But what we study like for OS, we mainly focus on some program we know, like something we expected to manage. But for all those like running in the background, we just like ignore it. We don't care about it. Yeah, okay. So what here is, so when you accumulate, so you can, it's just like trying to show you, okay, if we have like 3 different jobs getting in, then how it does like loading in the beginning. So the CPU, when they unit programmers, they do it one by one, do it slowly, and then multiple USC, it will be have an overlap. Just like taking, so we can handle of them like in the same time. Okay. And when we goes to the like multiple programming, like uni, just like finish this one, I go to next one. I finish the task, then I will add another new process and then finish it. But when we have like multiple different processes, then we need to like think about, okay, how can we share the resources? That means the controversy. Also, like how can we protect each program? We say like the application, we cannot like process affect other process. So how can we like prevent all those things?
One thing I just want. You go back to that.
Mm-hmm.
So here we've got them stacked on top of each other, which kind of implies we're running them at the same time. But I think we talked about that earlier, they're just back to back really fast. Right?
Yes, yes. This graph is showing like uni is like, okay, first I will do this first, do the next, and then last one. Okay, just like sequentially. But actually for multitasking, kind of yes. But we only, it's like we can handle multiple programs. So I can, instead of like I finish job 1, I will depends on like the income time, like when the process arrive. So I will put them into different small block. And then I will like taking, maybe we have different mechanism, like taking average time. So maybe each block we're taking only 1, maybe I put the unit, maybe 1 second like this, like I suppose like 1 nanosecond like this. 1 second, I will handle this process A first. If the time finish, then I will go to process B, process C, D, like this. Okay, it's like T maybe equals like until 4. Maybe I just need to have 1 second to finish process A. Then process A will be gone. So from T equals to 4 start, then I will handle process B like this, B, C, D. Okay, keep it like B, C, D, B, C, D, B, C, D. Maybe the D is complete, then I will just keep on working on like B and D like this. But when we look at it, they kind of like overlap in the same time. Maybe it's like kind of confusing. Just make it simple. Right now I open the PowerPoint and then also turn on the Zoom and recording three things, right? If we are doing the unit programming, it's like, okay, let me open the PowerPoint and then until I close it. If I don't close it or finish it, I cannot always open the Zoom. So right now you see like they are working in the same time. They kind of overlap, but in behind they are actually switching like all the process like in the same time. Like one by one each block. Okay. And timeshare system, that means, okay, we based on the time, so we will like share all the resources, and then we can like utilize those things. So we have can also support multiple user, so simultaneously access to a system through the terminal, and also when we execute, then we can like share all those like CPU and assign to this. And when we really compare with the batch programming with the time sharing, you see like batch, we just principle like for batch, we just the maximum, the processor use all the resources. But for the time sharing, it's like minimize the response time. So what's the minimize the response time is that when we do multitasking is that you feel like no delay to using all this application. And the resources like for the job control language commands they provide with the job. So really waiting for itself. Like if this the task will be handled by itself, but this one will be, if for time sharing, it will be like mainly handled by the terminal. So here's the difference. Let me go to case study. Okay, so the major achievement in the OS design. So we need to know, okay, what's the importance, and we're able to expand the major achievement of a history. Here's a same graph. We can see basically when we getting the, the capacity, right, goes up, and also we can provide, when it's more complex, we can deal with more like problems. Okay. First one is like about the process. We need to like how can we handle the process. Next is like how can we manage the memory and protect the information and security. And next, the last one would be how to handle with the scheduling, because like when the process or they comes in, and like which one go first, when they finish, which one go next. And this is how can we utilize the resources. Okay. As the first one, the process is a fundamental to the structure of, it's like really core, because we need to have multiple programs, then we bring them to the process. Sometimes you may confuse like program process. Process can be part of the program. So we break down the application like to small process. And those processes, we will do it as like taking terms like one by one. Because the CPU, even though it's a multi-programming, we have multi cores, right? Maybe 4 cores, but even each core, when we handle the process, actually they only can handle one instruction every time, just because they keep like finish one and switch to another one. So it looks like they handle it simultaneously, just like no delay. Okay. And when we try to handle the process before, like we always say we cause some kind of error. So one is like improper synchronization. So a program must wait until the data is available in the buffer. Or like we have an improper design of the signaling mechanism can result loss or duplicate. And it's pretty common, or like in our application layer, when we writing a program, let's say we need to waiting for input, or we fetch some data online, then it's pretty common, occurs the synchronization. If we need to read the data from the drive or memory, but if we don't wait for it, then it would be null. Have you write some program that says null input? Or like if you try to like pull something from the internet, that they say, okay, when you execute the next instruction, like get the download information, is it's no, it's empty. Have you write some program have this problem? No, okay. Mainly we are using like maybe some Node.js, we will do it, or like Python, we need to like put the like online information, or we need to get some input, but always because the processor already execute this instruction or like finish this one, but the data is not yet like arrive, the response is not come. So we always need to wait for it. Otherwise, we just have an error, say nothing exists. And then the fail mutual exclusion. So more than one user or like program attempt to make the use of shared resource at the same time. This really pretty common, and that's why we need to have a OS to help us to handle it. And only one routine at a time allowed to perform an update against the file. That's how we do. I think I use that pretty a lot, like the CPU power or like the memory. So we need to prevent is the data consistency. Okay, so if I read this input first, like, or read the variable, I read it, and then if I try to modify it, so are you going to okay, so one user is going to read it, one user is trying to write the data. Like I have one, let's say one instruction, maybe like one instruction read the data, one instruction is try to update the that variable. If we let them, how can we like manage these two instructions? Okay, so if I read it, and then for the next step, I let it to update, then is this reading is the old copy, or should I release the reading and then let it update, and then if next time we can read it again? So we need to have a mechanism that handle this part. Yeah, otherwise we have the data inconsistency. This is how it happen, and that's why it will causing the like some corruption, or like maybe some duplicate. Sometimes it did happen, like you allow like multiple writing. So we have two programs to assess it. Okay, I write value A, and then another one write the value B. So which one, or like are you allowing do it in the same time? That means like, okay, let's do it. Then program A thinking, okay, I will what I write is this content, like A. Then suppose I think this one I will store is A, right? That's what I expected. But if I didn't manage well, I let another process to update, change to B. Then they think, okay, it should be A, once B. When you try to match it, they say, why it doesn't match? Then it will cause the problem. So non-determined programs operation, sometimes the program will like the execution is interleaved by the processor where the memory is shared. So when we share the memory, that's where we say, okay, sometimes we'll overwrite from the memory, take a space. And then when the program execute, I will load it from the memory. So we get one piece of the data will be wrong. Also, the order in which the programs are scheduled may affect the outcome. So pretty common, it happen. What's the programming sometimes affect the outcome? Have you ever see sometimes the read write plus, because their sequence maybe no didn't see, because their sequence they are not going correctly, their output it doesn't go correct. Sometimes we write a program to simulate, it's like calling the next program. So when they calling it, so it's like which one is go first? They kind of like similar things. Like normally the next program will because it's in the stack, so we'll execute inside the next program or next function. If you didn't expect the next function will modify the value, then you think, and sometimes we have like as synchronized. So that means that, okay, it will modify the original memory address content. And then when you go to access it, then it's not the same. Okay. So it's kind of like this. And also the deadlock. So deadlock is pretty common happen in the process because we like more than suppose like we have two programs waiting for one for the output maybe, or like we are waiting for the each other. So but it's like it never comes out. So we enter a deadlock. So it's like no input, no input. So it's kind of like the system freeze. We always like see the most pretty common, we see the OS system like it freeze. It's like, okay, so we are waiting for the outcome, both of them, but nothing comes out. Okay. And as a component of the a process can be containing like three ones, like executable program and then associate data. So those data will be like need to execute for the program. Those can be some variable workspace, maybe in memory, or like some buffer we read into. And the execution content. So what's the process state? So what's the state of this process? When we go into this, really how to organize, then we'll know what's the state of it. And when we say the execution content is essential for, it's the internal data which the OS can able to like supervise and control the process. So we'll know it, and include the contents and various process register. So we know, okay, those register and which process go to which memory address and retrieve the data. And we include the information such as the like priority of the process and whether the process is waiting for the completion of particular IO event. Therefore, some process like or like part of the program, we need to asking for like waiting for input, or sometimes it have like higher priority, not the program, but sometimes like in the background process update, then we need to like take care first, then we can allow it to like go first. We do have a like mechanism to handle all these process. And when we manage the process, we'll know it's more like the address space right here. We know the start with the stack, and then here's like some like empty memory, and then we have the heap data and the code. So it's and in the process register, we can see we have the process index, the PC. So we have the like the program counter, and then we have the base limit, and then the others register we save right here. In the main memory, so you can see all the process lists will store, and some, if we look into the details, okay, some process lists will redirect to, okay, from this will be the another process because they're linking to another one. And all those processes you can see, okay, we have the context and we have the data, also the program itself, the code we need to execute. Those processes can be only part of it or like certain of the function. Okay. We call it the process, that means the unit of a resource allocate. So it's not the complete program. It's just like we break the program into part of it and for execution. So they do have their like own memory, and then sometimes they have like the file descriptor, file system content. So all these will save in the memory. And all these like process will encrypt one or more like threads or sharing the process resources. So they can share each other's. And that's why we call it processes. So they will like navigate the fundamental trade-off between the protection and efficiency. And also the process provide the memory protection while the thread don't. Yeah. So you remember the thread, do remember the thread cause is the action. Before we mention what's the thread. Do you still remember what's the thread?
The fetch and execute.
Yeah,
cycle?
not the fetch, but the thread.
Oh, threads.
Yeah, yeah. Yeah, the thread. Still remember. There's a graph like the thread is smaller. Do remember the wolf like thread? Yeah, so like those like action like maybe cause some possible, and they are more. So they were more like efficient than process. Process like the preset. They will come later than a thread. Okay. And those application instance consisted maybe one or more processes. So that's what we say. The application will break it down to different small processes. Okay. So we will try to go through the last will be this part, the basic problem of concurrence. So the basic problem of concurrence involves the resources. So the hardware, before we have a single CPU, single RAM, or one single devices. But why now for the multi-programming, then the process need to think they have like really access to all shared resources. So we need to have an OS tell us the coordinate. Okay, when we have multiple resources, how do we handle like taking terms? Also, we have the IO interrupt comes in. Then how can they keep their well? So we are using the virtual machine abstract and simple machine abstract for the process. So the unit programming, the one if you remember single line, and multiplex of this like abstract machine. So like then how can we do it all together? Looks like all together. And here's like kind of the illusion of a multiple processor. Because we share the memory, there's the main memory. Sometimes they can access the cache, like they all the CPU, the architecture. They normally the layer one will be like attached to the CPU itself, and then we are layer two outside of it. But just when I look at pictures, just like directly skip those parts. Okay, they will share all those memory. So in those like CPU, you can see maybe CPU 1, 2, 3 taking times, and then I go back to the CPU one. Normally in one single processor, then how do we just like put them together? They should like one block following each other's. And we will try to like put them in the stack. So I put out and then finish it, go to next one, put it out, next one. Okay. So based on time, I'm not going to the second achievements about the memory management. So we'll start by the processors right here. So first slightly boring, go to the lecture. I will try to looking something can like demonstrate how this like processor. Because later is more we'll talk about the mechanism, how those how do the OS like manage like when we have like start from time equals to 0, no process comes in. When we have my multiple process like come in, and then like how it take terms like based on different mechanism. So then maybe you know better about how to do it multiple. Yeah, it looks like as a result, like they just like have a display like the UI application provide you, but in behind actually the processor like just taking terms like finish each one, like part of it one by one, sequentially. Okay. And that's it for today's lecture. Thank you so much. Yep.
In yesterday's last time's lecture.
Okay.
There's a question asked. We were given cost of